definite one, like one quantized value. Instead, a quantum state, it represents a system where it can exist in a superposition until it is measured. Okay. Now, representation. Classical states can be defined by a position as well as a momentum at a given time. Slide not changed. Okay, I hope I have actually moved to the second slide where it is a key differences between classical and quantum states part 1. This is the heading of the slide. Can you all follow this? Okay. Okay. Then whoever is stuck in the first slide, I will request you just to rejoin again. I think that issue will be gone. So representation is when you can represent the system by position and momentum at a given point of time for a classical state. But instead of a classical one, in a quantum state, it is represented by a wave function. So it's a possibilities of multiple positions and and different types. So that is how you can represent it. Okay. Third one is very important. That is a determinism versus probability. I hope you at least understood what I mean by determinism and probability. Probability means a non-determinism in a very easy word. First. Now, determinism, if you remember that if I am in a particular state, if I have a particular output, these two things, if it is constant, then my output where I can actually jump to is a fixed one. Whenever it's a fixed one, it is called a deterministic approach. Whenever it changes or I have a possibilities where I can jump to. So I'm in a state Q, I have an input A, I can go either to Q1 or to Q2 or to Q3. Whenever I have multiple options to choose from, it is called a probabilistic approach or a non-deterministic approach, right? And of course, the latter one, that is a probabilistic one, is very much more computationally powerful than the deterministic one. But for that, what is the key thing? We have to devise a non-deterministic machine as well. Okay. Now here I just want to put 2 to 3 minutes on clearing a particular thing for those who are not part of like theoretical computer science and all those things, just so that you can have a better relatability. You guys might have heard of the like P and the NP kind of thing. We have those things later as well, but just to give you that one, whatever we do, say computing, it comes under different computational complexity classes, and we have very well defined 4 classes. First one is a P class, which is capital P. Second one is the NP class. Third one is the NP hard class. And fourth one, you can say it as an NP complete class. I'll be having it detailed way in a slides and all, just to give you a glimpse so that you have a better understanding at this point as well. So P problem, all of you might know the full form of it. It is basically a polynomial type. So we call it a polynomial time solvable problem. If a problem is in P. What is an NP? You will tell me, it's a non-polynomial. I just want to highlight 2 points here with NP. Just remember it. Have a note of it if you want to. NP is a non-polynomial only if you are doing it or you are, say, like implementing it in a deterministic computer. But it is basically non-deterministic polynomial. It is not non-polynomial. It is non-deterministic polynomial. The full form of NP, corrected form of NP, is non-deterministic polynomial, which says that if you have a non-deterministic machine, which is way more powerful than the deterministic machines that you have, then running that particular algorithm or logic or implementing that will take a polynomial time. So just remember, P was when you have a deterministic machine, you are getting it in a polynomial type. NP is when you have a non-deterministic machine or a more powerful form of machine, you can do it in the polynomial type. So in both the cases, you are doing it in the polynomial type. Just the fundamental difference is in one case, you have a deterministic machine. Second case, you have a non-deterministic machine. Also, just remember always, whatever we have, whatever devices we have with our classical setting, they are nothing but a deterministic machine. That is why we call that NP is those problems which take exponential time or non-polynomial time, because we do not have that access yet. with a classical setup to a non-deterministic machine. So rather, so in those cases, how we can proceed it? We cannot do it in a polynomial time. So it will be definitely taking something where the number of inputs or n, okay, or the scalability stuff, whatever you say it, it will be in exponent. Either 2 to the power n, 3 to the power n to the power n, k can be any constant or integer, k to the power n, likewise. Where the n or the function of n, f of n, will be at the exponent. I hope this is clear. Just keep it in mind. So NP is a non-deterministic polynomial and P is a deterministic polynomial. And NP is non-polynomial only when we have a deterministic machine. Now, since we have a deterministic machine, we call NP as a polynomial. I hope this is clear now, at least with till the point of P and NP. Okay? Okay. So, deterministic will be in for the classical state where knowing initial conditions allows exact prediction of future states. I hope it is very clear now. And quantum state, it's non-linear particles exhibit wave particles. Yes, but this is the logic or computing logic behind that. In case of that, in a case of a quantum state, it is a probabilistic where we can only predict the probability of finding a particle in a certain state. Okay. Now, depending on the inherent biasness, if the probability of finding, say, a particular state is 90% in comparison to another probability of finding a state which is a 10%, then for this kind of automated biasness, I can say that I will be getting the fast output because it's 90% biased. Those things are different. See, these are hardware loopholes that you have to refine or that you have to work on. But initially, if everything is all right, a perfectly noise-free situation, then it should be you are unable to predict what is the output. So, and this inability to predict or the unpredictability has a very, very beautiful application for a random number generator, where we've seen that a quantum random number generator is a perfectly random hardware setup which you can follow in order to get a okay. I'll be slow. I'll put my pace slow. Okay, sure. Thank you for this. So what I've said is, say, for this kind of an unpredictability, where I am unable to predict what will be my next step, just follow the third row and the last column. What it is written here, it is probabilistic, so we can only predict the probability of finding a particle in a certain state. Now, whenever we say it, that is, we can predict, means definitely we cannot absolute like convergence or say that okay, it will be definitely this state which we are going to get as an output, right? So it's a possibility. We can only predict the possibility. Now I mentioned 2 points. First point is, because we can only predict these, there can be, now imagine there can be 2 scenarios. First is I have 0 and a 1, on and off of anything it can be. Say I have a coin which I'm tossing. It can be, say, for example, for head, tossing the coin and I'll be getting the output head is basically 80% biased. Then tossing the coin and I'm going to get a tail. Now, in this particular scenario, tossing a coin is also a random experiment. You can get anything. So what you can do, you can only predict that what will be the output of probability of getting, say, head, which is 50% in an ideal case, unless you have a biased coin. If it is perfectly unbiased, if it is purely random, then it can be either 50% probability of getting a head and a 50% probability of getting a tail. Now, if it is like, say, Sholay movie, where no matter whatever you throw, it will always be biased and you will be getting a head. So that is a different thing. So unless we do anything like that, any form of this kind of tweaking happens. Okay. So what will we get? We can get a probabilistic or equiprobabilistic output. It can be either 0 or 1. It can be either head or tail with 100% same probability. Okay. But definitely it ultimately it's a probability, and we are doing it in the in that we are considering it's a very ideal setup only. that there is a very less amount of noise into it, very less quantum noise, no, really not that much of a quantum decoherence. If any one of you are missing the term, what is a decoherence and all, so I would suggest I'm trying to explain each and every term as if it's a modular session, but still, since it is very long, very lengthy, a lot of stuffs I have to cover. So might be you also have to follow the immediate earlier classes content. So if this is a new thing to anyone who has joined in the third day, I would request you at least go, if possible, once through both the recordings present in the YouTube. Then you will be getting what is the term explaining what. Bit of idea you'll be getting. So decoherence I already have explained, so I'm not explaining here. But we can do that, right? If it is no decoherence, no error situation, then you can actually cannot predict that what exactly your output will be, because it's a unbiased setup for a real quantum setting. Fourth one is a superposition. We do not have any way of doing it in the superposition. Just if you remember the 5-finger story of our hand, it's only 01001 that we can show. So it can never be a possibility where I can have a more than one kind of encoding simultaneously possible with my 5 fingers of my hand. It is not possible. So any form of superposition is not possible with any classical state. A 5-bit classical register can only hold one single value, 5-bit value, which is 01001. But a 5 quantum bit register or a 5-bit quantum register can store all the 32 values, right? So it can store 00000 till 11111, all these 32 values. Why 32? Because 2 to the power of 5, right? So it is possible. A system can be in a multiple state simultaneously. Next one is a measurement effect. So measuring position and momentum does not change the system state. Of course, we know it. For anything, it will be the like conservation of energy, mass, all those things will definitely be there, right? But in a quantum state, measurement will collapse the wave function into a single outcome. So initially, your like whatever was your quantum state initially, just before measurement, it will actually collapse to a particular outcome. Instead of holding that kind of a superposition or multiple possibilities together, it will now be into a single outcome. And this happens through measurement. So measurement also in a classical setting, in a quantum setting, is very different. Right? Okay. Next one is the wave particle duality. So in classical setup, we all know that a particles behave can strictly as a like particles itself. But for a quantum state, a particle, which can, for example, say a photon, that can exhibit both the wave property as well as the particle property. And through the 4 experiments, we've seen that how those evolution occurs through the black body radiation effect, Einstein's theory. It was a Crompton effect. Then it was a wave particle duality theory. So we've actually checked it. Okay, scattering effect of light of Compton. So we have checked this thing that it will happen. State evolution. So for a classical state, it is governed by Newtonian law of mechanics. We all know, and it's governed by Schrodinger equation. Today we will see what Schrodinger equation is. Uncertainty principle is another one. So in classical state, there is no fundamental uncertainty. Position and momentum can be known both simultaneously. For a quantum state, it is not exactly the same. Okay, it's governed by Heisenberg's uncertainty principle. And position and momentum cannot be precisely known at the same time. What is the theorem of Heisenberg's uncertainty principle? Then observability. Classical objects can be observed without altering their state. Quantum observability. Quantum observation will affect the quantum state, because while we will be doing the observation, we definitely have to measure it. Otherwise, we cannot observe it. Whenever we try to measure it, it will disturb the quantum system. So that thing will be affected. Neha Sharma, voice is not here. Is that the case for everyone else as well? Is there any issue with the voice? Okay, okay. Then Neha, please just try to rejoin. Okay, thank you. Thank you for confirming. Try to rejoin. How is observability different from the measurement point? It is not different, it's just a feature. Measurement is the act, and observability is the theory behind that activity, you can say. Okay, so observable is nothing but some operators that we will be doing it, but measurement is the act of applying those operators into in order to get a particular outcome, right? For example, so superposition is a theory that you want to do, but how we will be doing it? You will be doing it with a real quantum operator, which is a Hadamard operator. We will have a glimpse of it. So operator is that thing. Operator here is equivalent to an observable. Okay. And that theory is observability. So observable is one quantum operator, then you apply if you want to measure a particular system. And on measurement, because of you are applying an observable or a like operator, you will be getting at output only one state. It will collapse down to exactly one state. Why observation affects the state? In quantum, we can find the probability of error. We can guess the probability of error in terms of what I should be getting and what I am getting. So that difference will be your error. That definitely you can do. For example, I have just as I said, for example, I have a quantum, one qubit quantum system, which can give me either a 0 or a 1. And repeatedly, say for example, 10 consequent times, I am just trying to measure then what will be the output. Then what at the end I should be getting? I should be getting an equal number of zeros and ones. It can be random. I cannot definitely maybe predict that whether it will be a 0 0 0 0 0 1 1 1 1 1 or a 0 1 0 1 0 1 0 1. That we cannot do. But in an ideal setting, what it should be giving me? At least the equal number of zeros and ones. But in reality, with only 10 such iterations, you cannot guarantee that. So ideally, it should be 50% of 0 and 50% of 1. That is when we call that out of the 10 outcomes of zeros and ones, that particular bit string is purely random. So this is what we desire for. But in reality, what we might get all zeros, or we might get say 0, then all 1, say 1, then all 0, or any combination of 0 and 1. So if I'm getting such thing, and with respect to frequency, say frequency test is one of these statistical tests for randomness. If I just put a frequency as one of the metric, then what we will be getting? We will be getting, say, out of 9, out of the 10 possibility, maybe 8 out of 10 is 0, and 2 out of 10 is 1. So this is the probability of error, measurement error that you are getting, but you shouldn't be getting. Now, if you go beyond the, like, whatever you are getting, if you just go to the cause of it, you will see maybe one of the underlying qubits that is basically biased a bit hardwarely, you say, biased to 0. So no matter what you do, it will always be 0. Maybe for a few particular instance, just for a random thing, it happened that you have got a 1. Otherwise, most of the cases, you will be getting a 0. So that is an error between the what output you should be getting and what output you are actually getting. Error is nothing but that one, right? What your actual output and what you should be getting. The real output versus the actual output. Okay. Or say ideal output and the actual output, that particular difference. Okay. Now, entanglement. I hope observation and measurement stuff is clear now. So observation affects the system because measurement disturbs our quantum system. Now, entanglement is not present in any form in a classical state. So systems behave very independently, but we can actually create a kind of a dependency or a correlation. It can be a positively correlated as well as a negative correlated. We discussed these things through entanglement. So quantum states can be entangled, meaning particles influence each other, the way it behaves or the way or it produces the same output or a different output. So its entire behavior can be some way related to another, say, quantum state. In that way, they can be entangled, right? And definitely with certain kind of a sequence of quantum operators or quantum gates, we can actually achieve this entanglement. We can see that we are getting the same output. Say, for example, if I have in the qubits 1 and 2, these are the two qubits that I want to test. See, qubit 1 is 0. If it is 0, then qubit 2 will also be 0. So, a 0-1 state can never occur. A 0-1 can never occur. If 1 is 0, another has to be 0. And if 1 is 1, another has to be 1. This is a positively correlated. Okay? Now, very clearly, focus. I have two qubits. I have two, like qubit 1 and qubit 2. So initially, what was it? If nothing I am giving, no entanglement, it should be a 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. Because my first qubit and second qubit, they are perfectly independent if there is no entanglement or no correlation. But if I say that they are positively correlated, means I'm going to get the same out at both the qubits. So in this case, what will happen? The 0, 1 and 1, 0 possibilities will actually get lost into the system, and it will only be, we can only yield a 0, 0 and a 1, 1. So it is basically 1 over root 2, 0, 0 plus 1, 1. Why 1 over root 2? I'll explain it. As of now, just remember, out of the 4 states, it will now become 0, 0 plus 1, 1. Right? Now, similarly, for anti-correlation, a different thing can happen. You might also only get a 0, 1 and a 1, 0. That is, they are anti-correlated with each other, the output of the two qubits. If it is 0, it is 1, and if it is 1, it is 0. So if I have to tell it in form of a quantum system, I have to tell it it's a some amount of alpha, I don't know what it is, times Ket 0, 1 plus some amount of beta times Ket 1, 0. This is the anti-correlation theory. Okay? So this is entanglement. Right? The last one is the probability interpretation. Probability theory or these kind of theories actually arise from the lack of knowledge about the system. We do not have that much of knowledge. But for a quantum, whenever we are devising it, it will be very much, probability will be very intrinsic property because nature itself is very probabilistic. It itself is non-deterministic in nature, right? Okay. Now, these are a few things where I have actually used a pen and a paper. Go through it. I can see a certain, maybe a bit of blood or something. If you are having any issue, I'll be explaining everything. Don't worry. Okay. So if you want, you can write it down or later whenever you'll be referring it. I hope you will not be having any problem. Just focus here. So these are a few slides I've added for illustration. Okay. So one qubit quantum system, say for example, that system I'm representing with psi, which is nothing but alpha Ket 0. This is Ket 0. I've told you, a vertical bar and then some value within it in an angular bracket, closing angular bracket. This represents a Ket notation. Okay, so this is a Ket 0. So what is the interpretation of this thing? It interprets that it is a quantum system which is in state 0. Absolutely. Is this, first of all, I got two things. First is the audio breaking. I'm not sure about it. Anyone can confirm me on that. Is there any audio breaking? Breaks sometime. Audio is okay. Okay. So for those, please try to rejoin. Please try to rejoin. Okay. Uh, okay. Okay. Break. Please try to rejoin and let me know if this thing persists. Okay. 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 I got it. I got it. Okay. So as of now, I hope it is fine with maximum people. What this symbol is, definitely I'll be explaining it, Pooja. Definitely. I hope you are referring to has raised a hand. Please put it in on chat, Mansi. Just put it on chat. If you have a question, I'm waiting for your question, Mansi. If you're having any issue, yes, that I will be explaining, Pooja. Don't worry. Mansi also, okay, I'm just start with the explanation for Pooja. You happened by mistake. Okay, okay, Mansi. Okay, Mansi, no issue. Yes. So Dilip, I guess, is asked a question. So let me start with first his question. what it is, whether it is a quantum system or a quantum state. Answer is both. It is a quantum system with only one state. It is a quantum system with only one state. But it could be a quantum system with multiple states as well. So phi or psi represents a quantum system which is actually encoding only one state, that is a Ket 0. So this is a one quantum system and a one quantum state. Right? So that is why we calling it the quantum. It refers the quantum system is in is in state 0, which is a pure state. Why pure state? Because if we get only the purest form, say only 0, only 1, so it is like a purely classical setup. But at least definitely with quantum, I should be able to encode what we can do classically. So we can explain or we can encode only pure states. It is just that it is that you can encode a pure state as well as a mixed state, both through a quantum logic. The difference with classical is, in classical, you can only encode the pure system, pure state, but you cannot encode the mixed state. That is the difference. And for Pooja, what you asked is, what is Ket psi? What is psi? It is a wave function. As I just was explaining, alpha is a probabilistic amplitude. What is a probabilistic amplitude? I have not discussed yet. So you can think it of as a coefficient, that right now as a coefficient only. And Ket 0, this particular like a vertical line, then a 0, then this angular bracket. This is called a Ket 0. K-E-T, Ket 0. Right? I explained these things in like first 2 sessions or maybe in day 2. Just refer to that video, like recording or video as well. So we represent quantum states using this kind of bracket notation. So that is my Ket 0. Okay. Now, if I only have this Ket 0, not Ket 1, then it is only one quantum state, and that is only one quantum system of one qubit, which has one state. Believe I guess right now it's clear. So it's a one quantum system which has only one state, right? But it can definitely be more than that. We will be having those things into our explanation. Now, but definitely, what is the probability of this get being in a state 0? If I have only one state, so I have a definite probability of going to that state. So here, probability and definiteness, they will merge if I have only one pure state. So it will be definitely 100% probability, right? So these particular thing like Ket 0 can be represented by alpha 10 in a column vector form. Just refer to it. Everything is mentioned here. So 10 in a column vector form, where 1, the upper one is the position, interprets 1 in this position interprets that it is high for Ket 0. Don't mix it up, both the things. In a column vector format, wherever on top you are getting a 1, this means that it is representing that it is high for Ket 0. Okay. So 0 should not be encoded with 0, 1 should not be encoded with 1. That is not the logic. It's just the respective positions. And here in the column vector format, every position has a definite meaning. So whenever I have a 1 over here on top, it says that 1 in this position will interpret that it is high for Ket 0. And the lower 0 in the column vector will represent that it is low for Ket 1. Because on top generally we represent for a 2 cross 1 column vector. On top we represent with a what? With a basically Ket 0. It is the top position, and the bottom position is actually some representative of Ket 1. So if that is 0, that means Ket 1 is not there. And if the Ket 0 1 was 1, so that means Ket 0 is actually here. This is a dilemma. I hope it is clear now. Don't mix up both the things. This is a position referring to which particular quantum state it's on at that given instance of time. Okay, this is just representing a position. The column vector only represents a position, right? Okay, now similarly, if I have, say, phi is equals to beta times 0 and 1, where 0 is on top and 1 is at bottom, what it will represent? It will represent a quantum system with only one quantum state. And what is the quantum state? It is Ket 1. And since only Ket 1 is here, no Ket 0 is here, so we call it a pure state. Okay, so my quantum system can be anything. It can be either a pure state or a mixed. Okay, but say for example a case where I have both the things. So now my phi is basically alpha 10 plus beta 01. Explain again a high and a low meaning. Okay, high and low means it's basically represents an on and off thing. So it means whenever I have on top I have 1, it means for Ket 0 is on. I don't have a Ket 1 here. Position not clear. Okay. It will be cleared as a very process with multi-qubits like state representation as well. For now, it's only a one qubit representation, which has a two definite places. That is why it's a 2 cross 1 column vector. So the first row, first column represents a 1. And a second row, second column represents a 0, means the first row, first column. Now remember position. First row, first column for a 1 qubit system will always correspond to Ket 0. And second row, first column in a Ket vector notation or in the column vector representation will only interpret, or it can be interpreted as a like Ket 1, position to represent Ket 1. The similar thing you are getting here. Okay, exactly similar thing you are getting here. Just for an example, just to clear these things, let me give you this thing. We'll understand it. Okay, just understand this thing. So this state is totally depending on time. If we remove time, you cannot remove time. That is not possible. Time is, you cannot reverse the time back, but definitely you can reverse back the operations. That is the reversibility theory. I will be, yes. Definitely. It is also like not disturbing the flow, but if it is like very basic thing, I think clearing these things right now will help the others to understand it as well. But if I find the questions asked are not really very relevant to the context that I am currently telling, I will definitely love to take those questions at the end through chat. Okay, let us follow this principle. So basically just see the example of say 0, 0, which is a 2 qubit system. So we can check it like on top. Now 2 qubit can be represented with a 4 cross 1 column vector. If it is 3 qubit, it's an 8 cross 1 column vector, likewise. So I have a 1, 0, 0, 0 in the column vector form. Now what on the top 1, what it is representing? That is the position for 0, 0. That is why I'm getting a 1 over here. Everyone please confirm this thing, whether you are understanding this particular part or not. So 1, 0, 0, 0 in a column vector form, what it is representing? It represents that I have a 1 in the position of 0, 0. This means it is only Ket 0, 0 that is being represented over here. Now similarly, just go and check for the 0, 1 Ket notation. Okay, when I have to represent a 0, 1, I can do it in form of a 0, 1, 0, 0. The second row, first column, that is the second position here in the column vector is a representative for 0, 1. That is why I'm getting a 1 over here. It shouldn't be any confusion right now, because in column vector I can represent only 0, 1, but depending on what is the respective position of that particular state, which has a correspondence between the position and the decimal value of the state, there only I'm putting the values. I hope it is now clear. So 1, 0, that can be represented with a 0, 0, 1, 0, because the third row, first column 1, that particular position is a representative of 1, 0. And all these notations, either it is in a column vector notation, or it's a Ket notation, or it's a Bloch notation, everything they're equichangeable, or like they have a similar kind of meaning. So it does not matter in what format you will be asked questions about, or you might have to read a paper, they can use any notations, but you should be able to map the differences between these things, because the Ket notations, although these are part of a Dirac notation, it's an abstract notation, but in actually, for if you have to compute, you cannot compute directly with the help of a Dirac notation. You have to break it in the normal algebra that we do. So it is a way, it is basically position here now. Yes, I'll explain it. So it is a way we actually start encoding something and do certain computing once I have the encoded thing. Because honestly, what is a bra zero or a Ket zero? What does it mean? Or what is a Ket 00? What is the interpretation of that thing? How to understand it through our logic, or how to put our logic into it. For those things, we need a simple linear algebra things. And this is a like matrix format, wherever our quantum state, as well as any quantum gate, as well as any quantum operator, everything can be represented by what? By this kind of matrices format, or through the linear algebra. That is the thing. And how position is related, or why we need this kind of position thing, is that because whenever we will be multiplying, how to interpret the output from the input or from the operator. So in order to get what is the output, we actually, I think recording will be shared with all of you. So we think actually, in order to interpret the output, we need that what that particular position in the output matrix, the final output matrix actually represent. So that kind of backtracking, whenever we'll be trying to do, we can do it if we represent it through the positions. Okay. There should be we should be having certain mapping between the quantumly represented notation and the way we actually can compute it, because we have to think it right. So for that briefing, we are actually using these kind of things. Now say I have Ket psi is equals to 1001 in the 4x1 column vector. Now, I hope right now you're understanding that the top one is representative of Ket 00, and the last one, the bottommost one, is a representative of Ket 11. So if I have only this thing in the column vector format, now both the things we are doing. So from LHS to RHS, we have right now seen that from the Dirac notation, can I map it to the column vector representation? Yes, we can do that. That is very easy. Now the reverse thing. If I have it in a column vector format, can we go back to the Dirac notation format or the wave function thing? Yes, we can do that. How we can do that? It's basically like the same thing. It's only 1 for 0, 0. So it's alpha 0, 0 plus beta times 1, 1. What is alpha beta? Again, it still is in a masked way. I do not know what is it. But definitely if you want, or this 1001 you can write it down as alpha 0, 0 beta. Because 1 into alpha is alpha. And only alpha can also mean like alpha into 1, which is alpha times Ket something. That is what we are doing. Okay. And if I have 1010, it is alpha 00 plus beta 10. If I have 100 minus 1, that is, it is alpha 00 plus minus of beta, because minus of that is the only like 0 and 1 can be either on and off. So from where the minus sign is coming into picture. What does it represent? It does represent certain form of phase. Let us now not consider what a phase or how complicated a thing is. Right now, we are only focusing on a high and a low thing. So on and off. So it is basically a 1, 1 with a minus beta. And it's a positive superposition of all these kind of possibilities. So it's alpha 00 minus beta 11. If we have right now, say for example, psi equals to alpha 00 minus beta 11. And if I ask what will happen in the output if I just apply an Hadamard operator, what is Hadamard? I do not know. So I might ask you questions like in this way. Say I have a quantum state psi that is represented by a two-qubit system, of course, that is represented by a alpha 00 minus beta 11. What if I apply a Hadamard operator onto it? Can you tell me what will be the output? So these type of questions I might ask you. For that, you have to first represent the alpha 00 minus beta 11 in the matrix form. Then you have to think what will be the equivalent Hadamard matrix, or as a quantum gate is nothing but a quantum operator. Operator is nothing but a matrix here. So how these things will actually flow? For that, you have to represent your matrix, Hadamard operator or gate in a matrix form. Now, it is now right now. Once you have both the matrix forms of both the things, it will nothing. It will be nothing but the matrix multiplication. Now, matrix multiplication will also give you one result. So from that result, again, you have to like decode the meaning of it, that what the final output will represent. Whenever we'll be doing it, there I will give you like ample amount of examples for that. How and also like whatever matrix multiplication, how to interpret the results, all those things I'll be giving to you. So those things will be clear at that point. Okay. Now let me just go back. What minus is representing as of now, you can think it of as a negative coefficient that is associated with the state 1, 1. That is the way you can think it of right now. Okay. But if you want to know, it's basically the phase associated. So we can actually make the 1 as an inverted 1, right? That we can do. I guess, yes, the first slide is over and the last slide is also over. So now focus very carefully here. Very carefully. So both the pure state things we have seen it. Like for a 1-qubit system right now, say if I have like phi equals to alpha ket 0 plus beta ket 1. That is, it's basically alpha times 1 0 plus beta times 0 1, which is nothing but alpha 0 plus 0 beta is equals to alpha beta. Okay, so alpha beta both values present in the column vector form means it is a pure state. If there is only 1 in the column vector, all the other states are 0, then it can be any big state, any big column vector with any number of rows, but it will always represent a pure state. For example, if I have, say, 0, 0, 0, Ket notation, how it will be represented in the column vector form? Only on top it will be 1, then 7 zeros on bottom of 1. But since there is only 1, 1 in the column vector, we call it a pure state. But if it is like multiple ones, we call it a mixed state. So pure state and mixed state has nothing to do with the number of qubits. Even a 1-qubit system can be, say, phi equals to, in the column vector form, it is 1, 1, which represents both 1 into a single quantum system. So it's a mixed state. But if I have, say, phi is equals to ket 0, 0, 0, then it means it's a pure state corresponding to the values 0, 0, 0 ket. That is the logic. So don't mix up the mixed and pure state with respect to the number of qubits. It is only understood from the number of ones when it is represented using the column vector format. Clear? Okay. So have a very crystal clear understanding of these kind of pure and superposed state and number of qubits and number of states. Well, how to represent a state. All these kind of things should be very, very clear to all of you. So alpha 0 plus beta 1 is representing a mixed quantum state where alpha square and beta square are the respective probabilities of the quantum state phi to be in ket 0 and 1 respectively. That is alpha square. What was my quantum state? It was alpha ket 0 plus beta ket 1. Just check it. It was here. It was alpha ket 0 plus beta ket 1. But what I'm calling now? I'm calling that alpha square is the probability that my quantum state phi will be in ket 0. And beta square is the respective probability associated with state 1. Right? It's not alpha beta. And why this is happening is this happens because of the normalization constraint. We call it alpha square plus beta square. Mamta, my voice is not audible. Is it audible? If host once can confirm it. Okay.
Yeah,
Then
no
Mamta,
problem.
please.
Actually, clear, very clear, ma'am. No problem.
Okay.
Please check at
Please
your end,
rejoin.
please. Yeah.
Yes. Okay. So the square of the summed, the summation of the square of the amplitudes is basically, it should be 1. So alpha square plus beta square should be equals to 1. Because why only these two, alpha and beta? Because I have just told you that I have two states, 0 and a 1, and this entire thing, like phi is one mixed state. So it's a one mixed state or one superposed state consisting of two pure states, where each of the pure states respectively has certain probabilities associated with it to be in those pure states. And what are those probabilities? Alpha square and beta square. But if I want to represent the mixed state itself, it will be alpha times Ket 0 plus beta times Ket 1. Okay? So alpha and beta and alpha square and beta square, both like these both pairs are very, very different. Only alpha and only beta, they represent the respective probabilistic amplitudes of states 0 and 1. So remember, alpha and beta, they are not probability, they are nothing but certain amplitudes associated with the probability. And from a very, like, I will not go into very detailed of it, but just you can think it of like a plus and a minus thing. So basically it's a variance. It can be plus, it can be minus. That is why for probability, we put it like a alpha square and beta square one. Okay. And alpha and beta, they are just respective amplitudes. Now remember, I have just also mentioned over here, remember alpha and beta are not the probabilities themselves, it is rather alpha square and beta square which represent the probabilities. For example, say I have phi is equals to 1 over root 2 Ket 0 plus 1 over root 2 Ket 1. That is nothing but a 1 by root 2 Ket 0 plus Ket 1. Just taking 1 by root 2 as common. These interprets a few things. So what are the possible interpretations? Let us just do that. First is the probabilistic amplitudes of Ket 0 in phi as well as the probabilistic amplitude of Ket 1 in phi. Both are 1 by root 2 because my alpha and my beta both are 1 by root 2 here. And probabilities of phi to be in the state 0 while it holds a superposition is half, that is 50%. And similarly, because it's a like 1 by root over of 2 for both the cases, it will be like a 50% of case probability for Ket 0 and a 50% probability for Ket 1. Now say I have given you a small tricky question where I've given that phi is a quantum state. It is psi. Say phi is a quantum state and it is represented by, say, for example, half is the probability, or say it is half is the probability of the Ket 0 and half is the probability of Ket 1, then 50-50%. Now, what will be the corresponding coefficients of coefficients associated with Ket 0 and Ket 1, both? If you tell me since it's half Ket 0 plus half Ket 1, it will be wrong. Yeah, absolutely. So just remember it is 1 over root over of 2. I'll be giving another example where you will be calculating it, you will understand it. What I mean is, so if a quantum state under superposition is equiprobable for all of its substates, it is called an uniform superposition. Hadamard will show that right now. Hadamard creates the basic superposition. Yes, so once you have a pure state, if you want to get a mixed state, the very first and irreplaceable like thing that you have to do, you have to first begin with a Hadamard, because Hadamard creates superposition. Okay. So, but if it is equiprobable, we call that particular superposition as uniform superposition, as I have seen it over here, 50% 0 and a 50% of 1. Okay. And if I say, for example, alpha square, that is the probability of getting Ket 0 is 70% and beta square is 30%, then this kind of scenario is called a non-uniform superposition, or they are non-uniformly superposed. Okay? Now, say it's a small numerical example. I want all of you to solve this particular problem in your kind of rough sheet. Just tell me what will be the answer. The question is, I'm just reading out for all of you. Say I have a quantum system, a very simple 1-qubit quantum system, where the probabilities of the system to be in state 0 is twice the probability of it to be in 1. Okay. Now, if the system is represented using psi is equals to rho 1 times Ket 0 plus rho 2 times Ket 1, please calculate the respective values of the coefficients rho 1 and rho 2. Just please solve it. I'm giving all of you 2 minutes of time, 2 to 3 minutes. Just post it on chat. I will then verify whether it's correct or not. Please, everyone, just have 2 minutes of time. I'm giving you. Try to solve this question. Find the values of rho 1 and rho 2. Another 1 minute. 0.7 and 0.3. A lot of values are getting. If I could listen from all of you, that would be good. But I don't think in WebEx we have that particular feature yet enabled. And what is your thought process behind these things? I'm getting almost very diverse outputs. So only one is correct, maybe, and all of you are wrong. Just recheck once. Have 1 more minute. Just check with whatever you have just learned, the theories and all. It should match everything. 2 by square root 3, 1 by square root 3. A lot of values I am getting. Okay. It's time to reveal the answer. Sure. Let us do it like normally. Forget about what is it. What is what. So probability of a system to be in Ket 0 is twice the probability of it to be in 1. So say for example, probability of it will be 1 is x, and probability of the system to be in Ket 0 is 2x. So 2x plus x should always be 1, because probability should always be like summed up probabilities should never exceed 1. It's exactly 1. That is a normalization constraint. So it's basically x is equals to 1 by 3. That is the probability of being in state 0 is 2 times the probability of being in state 1. So x was 1 by 3. So probability of 0 is 2 by 3. And probability of 1 is 1 by 3. Till this part, it is okay. So the probability is 1 by 3 means basically 0.33333, something like that. And 2 by 3 is basically 0.67667, something like that. Now, what I have asked you, that if the system is represented using psi equals to whatever, rho 1 times Ket 0 plus rho 2 times Ket 1. Rho 2 times Ket 1. Just check. I don't know from where you are getting 5 thing here. How 5 square root of 5 can come once? It is no way related. So how can 5 come? Yes, absolutely. So what was my rho 1 and rho 2? If I have a system like this, phi equals 2, so what should be my probability of getting Ket 0? That should be rho 1 square, right? And what initially I got as a probability? 2 by 3. So if rho 1 square is equals to 2 by 3, and imagining that I do not have a consideration of an imaginary root and all those things. So square root of 2 by 3, we have to do. So it can be either plus root 2 by root 3, that is plus square root of 2 by 3. Square root, many of you are writing like 2 by square root of 3. It's not right. It will be root over of 2 by 3. Square root of 2 by 3 itself as a whole. Okay, and it should be square root of 1 by 3 as a whole. I guess first the right answer was given by Amit. He actually mentioned the same thing, like square root of 2 by 3 and square root of 1 by 3. Those will be the respective values of rho 1 and rho 2. Clear? So this is the explanation. Solution to the problem. Say probability of 0 is twice the 1. Say probability of 1 is x. Probability of 0 is 2x. So from normalization constraint, we know that 2x plus x is equals to 1. So x equals to 1 by 3. So probability of 1 is 1 by 3. Probability of 0 is 2 by 3. So rho 1 and rho 2 will be nothing but probability. Rho 1 square is the probability of 0. So rho 1 is square root of 2 by 3. and row 2 is square root of 1 by 3. Now, if you check the value, it will be somewhere, it can be anything like root 2 by root 3. Consider root 2 is 1.414, root 3 is 1.73 or 2 or something. Just put the values, you'll be getting something like that. So are you getting it? The probability of being, now say you have the last line, just see the last line, say phi is equals to 0.8163, or I give you only say 0.82 Ket 0 plus 0.58 Ket 1. If I ask you now that what is the probability of this particular phi state to be in Ket 0, if you tell me at that case it is 81.63%, and one is probability of getting 1 is 57.7%. Just try to add them up and check if it is coming anywhere like similar to 100%. Yes, Mahadev, I have added the illustration or everything in the slide itself. Okay, I could have added a letter, some other thing, or maybe I was thinking that whether I should be giving it in a separate file or I should like put it in an image, everything in the slide itself. So I thought of like this one may be more beneficial. Then you will be having per day, you will be having one lecture content with all those things.
Yeah, actually we discussed, and madam suggested that she has created an image for everything. She has handwritten, created image and pasted in the slide. So everything will be shared with you, right? Yeah. Thank you, ma'am.
Yes, yes. So just check from here. So 81.63% and 57.7%, they are not same. That they do not anyway add up to 100%. So these are the probabilistic amplitudes. So it's a kind of a normalization that we are doing with respect to the probabilities, because we cannot exceed the maximum probability of being like exceeding one. We cannot exceed this particular constraint. So keeping that thing, okay, so we initially started with the probability, then we tried to normalize it when it was in superposition, and we checked that this is the only way it will work. So probabilistic amplitude is that particular kind of way to represent all these things in superposition. But probabilities will be the summed up of the, the squares of the probabilistic amplitudes. Here total is more than 1. It is a probabilistic amplitude, they are more than 1. I do not have any problem with that. But what I have told you, if you just square 0.8163 and also add it with the square of 0.577, you will check it will be somewhere similar to or approximately similar to 1. Because for the decimal values and all those things, maybe a bit of something very minimal thing that can happen, because I have used just normal calculator and all. But if you do very precise calculation, it will be exactly 1. Okay. Now a 2-qubit quantum system. 2-qubit, 1 qubit, we have checked everything. How it is related, what is the meaning of it, where, what position, how position is very important in the column vector, all those things. Say for example, right now I have a 2-qubit quantum system. That 2-qubit means how many states I can represent? 2 to the power 2, that is a maximum of 4 quantum states. Now my phi can be anything, either it can be 0, 0 or it can be 0, 1. So it's, let me call it Ket 0, 0, Ket 0, 1, Ket 1, 0, Ket 1, 1, which is the 0th, 1th, 2th, 3th position. Okay. Now, if I want to put all the 4 states as a superposition or as a mixed state, now, Dilip, I guess you asked initially this question. So what is the, how many quantum states? What are the quantum states and what is a like quantum system? So it is 1 2-qubit system. How many system? 1 2-qubit system, where phi is a representation of a mixed quantum state, where how it is mixed? It is mixed with alpha square probability with voila 0, 0, which is a pure state, plus beta square probability wala 0, 1, plus gamma square probability wala 1, 0 state. So this is another pure state 1, 0, and delta square probability wala 1, 1. So all these 0, 0, 0, 1, 1, 0, 1, 1, all these 4 are pure states. But they all together with a certain probability when they reside. This is a simultaneous explosion of possibilities that we were discussing from the very first day. If I'm able to do that, so that can be also represented by one single quantum state, which is phi. So phi is equals to alpha 00 plus beta 01 plus gamma 10 plus delta 11 is one quantum state, which is a mixed state. Which is a mixed state. No, till now there is nothing related to entanglement I have talked about. These are normal superposition. These are very normal superposition. Okay. I think there was a doubt with the previous one. Just take with the slide. I think it will be clear. No issue. So if now psi is in a uniform superposition, and I have 4 states, so definitely probabilities will be what? Probabilities will be 0.25, like 25%, that is 1 by 4 should be the like thing. Probabilities 1 by 4 into 100, which is 0.25. So if 1 by 4 is the probability, that is if alpha square, beta square, gamma square, delta square, all of them are individually 1 by 4. So that sum of alpha square plus beta square plus gamma square plus delta square is equals to 4 into 1 by 4, which is nothing but 1. What will be the individual values of alpha, beta, gamma, delta? That will be square root of 1 by 4. That is square root of 1 by square root of 4. That is 1 by 2. So that is why half Ket 00 plus half Ket 01 plus half Ket 10 plus half Ket 11. All these half represents the probabilistic amplitude. But they have a probability of 25% for each of these basis states. Okay. Okay, great. Now this slide I already explained, this one. Yes. Just a few more interpretations. Say illustrations. Say phi is equals to 1, 1, 1, 1. Now all of you know, if I have a column vector, 4 cross 1 column vector with 1, 1, 1, 1, what it can possibly interpret? It will interpret alpha Ket 00 plus beta Ket 01 plus gamma Ket 10 plus delta Ket 11. Forget about alpha, beta, gamma, delta. How it is coming? The first one is coming from, because 0, 0 is nothing but 1, 0, 0, 0 in a column vector form, plus 0, 1, 0, 0 plus 0, 0, 1, 0 plus 0, 0, 0, 1. It's a simple matrix addition of 4 very simple column matrices. Just add them up, you'll be getting 1, 1, 1, 1. Of course, it is a mixed state. Of course, this is a mixed state. Now, here I just have like told you that, okay, say for example, this one, phi equals to alpha 0, 0, beta 0, 1, gamma 1, 0, delta 1, 1. So this is the same thing. So it does not matter that in what way I represent it. If I represent it in this way, Dirac notation, say algebraically Dirac notation, phi is equals to alpha 0, 0 plus beta 0, 1, gamma 1, 0 and delta 1, 1. Or if I just give you this particular thing, only 1, 1, 1, 1. Both the things represent the same thing, right? Again, with respect to positions. Got it? So Ket notation is nothing but, I hope Dilip, your doubt is like clear. It's the same notation, just an equivalent representation. Okay. Okay. Just one person has certain doubt. Let me clear it. CC1104. Whoever you are, you might missed the question statement once. Let me tell you what was the question here. It's not only the probability is x and probability square will be x square. So it's basically 2x square or something you have done maybe. So don't do that. Maybe from that you are getting 1 by 5 or 5 thing into picture. Just check it. The probability of states 1 to be in 1 was x and probability itself was in a square thing. Okay. So it is itself in a square thing. So maybe you are just mixing it up and making that x and 2x and it is like 4x square. So why you are picking x as the probabilistic amplitude and then for probability you are summing like squaring it up. So that is why you're getting x square and 2x whole square, you are getting 4x square. So 4x square plus x square is equals to 1. So x square equal to 1 by 5. That is wrong. What I have told you, like probabilities of the system itself to be in state 0 is twice the probability of it to be in 1. So probability itself I have given you. That is x. Probability is x. So the probabilistic amplitude will be somewhere root over of x. That is why for like Ket 1, you are getting the 1 by 3, 1 by root over of 3 as row 2. Okay. Okay. Great. Okay. Yes. So the first line is over. We do not use probabilities, otherwise we cannot represent it in the normalized way. That is why you cannot use it. Because a wave function itself says that it has to follow Schrodinger equation and it has to follow the normalization constraints. So that is why we represent in this way. But whenever you will be like measuring it or understanding it, what is the probability associated, you have to do the squares of the amplitudes. So Ket notation is 0, 0 is equals to 1, 0, 0, 0. And Bra notation is the dual representation of Ket. Both are like direct notations, the bracket notation, but the Bra and Ket both are like dual of each other. So Bra 0, 0 will be represented by this thing. First, the opening angular bracket followed by your thing like 0 or 0, 0 or whatever you want to put, then a vertical bar. So it will be nothing but instead of initially it was a column vector 1 0 0 0. Right now it will be a row vector which is 1 0 0 0 in the row vector form. Okay, so it has how many? What is the number of row and matrix? What is the dimensionality of this thing? It has a 1 row and 4 columns. So it is 1 cross 4. Okay, column vector 1, that was 4 cross 1. Okay, okay, till this point. Absolutely. It's a transpose of Bra vector. That is why you called it dual. But the thing is that is why alternatively you can also write like Ket 0, 0 is nothing but if you have it representing it in the row vector form, just a transpose of it. And these are all the useful notations where in a like diverse way you will be checking. Maybe in a research paper they are following a certain kind of format. In some other like reference books, everything, so that I just want to have a like bridge between all these terms that they mean the same thing. Ultimately your target is to extract the information that it is trying to convey through those notations. So be it in any way, that is indifferent, you have to extract the exact information. Got it? Okay, so similarly if I just give you Bra 0 0 0, it will be 1 1 1 0 0 0 0 0 0 0. Okay, and if I give you Ket 0 0 0, so it is Bra 0 0 0 transpose of that one. So for a 2-qubit system, this is a corresponding representation. And for 1 1 0, if I give you a Ket notation of that, so it will be 0 0 0 0 0 0 1 0. You know why the 7th position is 1? Because that is the representation of 1 1 0. Considering we are starting from 0 0 0, then 0 0 1, then 0 1 0, then 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. Since I have 1 1 0 over here, so it will be 1, and that will be a transpose. That is Ket 6. Okay. Also one thing. Now I want all of you to think. I just have mentioned 7th and 8th position is not the one. 7th position is basically for 6th. Considering I have started from 0 0 0 to 1 1 1. You can check that there are 8 values. So that's why the last 2 values maybe you're asking 7th and 8th. That thing is like coming into picture. Okay, now very important point. Just focus here again. In the last class, day 2, I mentioned one thing. That is our Ket notations are most widely used notation rather than the Bra notation. Okay, if you remember, I have just told you these things. Now, if I say you, I have a quantum state which is, say, for example, 0, 0, Ket 0, 0. Okay, I want to apply a quantum gate on top of it. What are the instant information that you can extract? That Ket 0, 0 is 1 0 0 0. Great. Okay, now I'm asked that I might be like having a quantum gate that will operate on this state. So then it should come in your mind in this way that, okay, now quantum gate is nothing but a quantum operator, and any operator is nothing but certain matrix. Okay, so what will be the matrix? It will be generally for quantum always a square matrix. That is a m cross n thing, right? Now, if it is a like either it can be 2 cross 2, or it can be 4 cross 4, or it can be 8 cross 8, 16 cross 16. Likewise, it will move on. Okay. So if that is the case, and if I just multiply this operator, which is say, for example, for a 4 cross 4 Hadamard, maybe I have to use of like 4 cross 4 Hadamard matrix, which is 4 cross 4. And these Hadamard will work on the column vector, which is say one column vector on one column vector of say 2-qubit system. So it's basically 4 cross 1. So 4 cross 4 and 4 cross 1, they can be multiplied. They can be multiplied. So the basic theory of matrix multiplication says that the column of first matrix and the row of second matrix under multiplication, they has to be the same. That is when we can call it, that is, it is a multiplication compatible, everything and all those things. So that is why, because generic, in a generic setup, we always have a like a quantum operator which is in a matrix form, and with using those we compute all the calculations. So we prefer Ket notation over Gram notation. That is our basic assumption. Okay, great. So here we are ending the illustration part. Now, anyone want a 2-minute break now? We have half an hour more. Great. Let's just meet just after 2 minutes. Have a small like have some water and all, then just come back. We will start right now. It's 3:30 almost, so we will start again from 3:32. Okay. Okay. Yeah.
Hello, Nivedita ma'am. Ah, we will just wait. I think ma'am is, there may be some issue. We'll just wait. Okay. 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 It's a break. Yeah. Thank you.
Yeah.
Ma'am, we'll take a break,
Yes,
just
sir.
1-2 minutes. We can start after 1 minute, 2 minutes.
Sure, sir. Yeah.
Yeah. The participants have requested. Maybe they are also taking a break. Just
Okay. Okay. Sure.
1
Sure.
minute, and then you can start. Or if you want to repeat something, you can go ahead.
No, I'm just waiting for 2 minutes.
Yes, ma'am. We can start, I think, ma'am.
Yes. Yes. Okay. So So these are just the theoretical, a certain kind of a description of what we have learned. We have learned the meaning now. Now I will just, we will just go through a different kind of like certain formulations or the way we actually describe the quantum system or the like wave functions, everything. Okay. So what is a wave function? So phi xt, it's a complex valued function that varies with position t. And it does not really give directly the physical properties, but encodes the probabilities of different measurement outcomes. We have a very well-defined set of understanding with this thing, I guess, that it is not exactly any physical property, but we are encoding the possibilities or probabilities of different measurement outcomes. So analogy is just like a musical note that carries potential for sound. Phi xt carries potential for different measurement outcomes, just like a music wave or musical wave. So phi xt as a probability amplitude, and the square modulus of phi xt gives the probability density of finding the particle at position x at time t. You are understanding. Don't get confused with more of the like Greek symbols and all. You have understood the value. Now, simply the interpretation wise, the probability of xt is whatever the phi value you are getting for that particular, say, outcome, the square of it. That is the probability. And definitely, as high as the probability will be, it will be, or it will arise, that will be the probability of finding that particle. That will also be high. For example, say phi is equals to 70% of 3, 0, and 30% probability of having a 1. So it's basically root over of 0.7, Ket 0 plus root over of 0.3, Ket 1. If that is the scenario, then we can tell that mostly in the outcome, zeros will come more. The frequency of having 0 will be more than that of 1. So, and that probability is nothing but the probability of finding that particular particle. Okay? That is probability of obtaining that solution, or probability to ultimately reach to that particular state as output. Any way you want to encode, you can encode it. But ultimately, it's the probability of that particular, associated with that particular pure state. Okay? It can be complex. It can have a real part as well as an imaginary part. Definitely, it can be that. Okay? However, the observable physical quantity, the square is always real, and that is always positive. So the probabilistic amplitudes, that can be actually a complex thing as well. And phi xt, what's it? Okay. The wave function, yes. So phi xt evolves in time. The wave function changes over time according to Schrodinger's equation. Physical meaning of imaginary part, yes. So those things will only come with respect to the representation of the basis or the pure states in together. So it's better if I just show you one diagram, you can understand. Just a minute, let me just check whether that diagram I have given over here or not once. Maybe not today I have given that one. Okay, yeah, not today. So it is basically, say for example, just consider it in this way. There is a 3D ball, a 3D sphere that we have, a three-dimensional sphere, solid sphere. Okay, where a few part of the like the surface of the ball actually can represent any position associated of a particular particle that can reside on that ball. Okay, so every particular position, Bloch sphere, absolutely. So every a bit of, like any position can have a, with respect to different coordinates, that has a particular position vector. Now, whenever we do that, what we do, that particular 3D ball or 3D sphere in quantum mechanics, that is called a Bloch sphere. BLOCH, Bloch sphere. Okay. Now, if whenever we try to put a value or plot a particular position of a particle onto that Bloch sphere, we take help of different axes. So there is different axes give us different measurements for the same value. Okay, say for example, I have a certain thing and I want to measure it with respect to the XY axis. I'll be getting one value. With respect to YZ axis, I'll be getting one value. With respect to the ZX axis, I'll be getting one value. And all these three axes is present simultaneously onto the Bloch sphere. Okay. Now I'll be getting another value. Now, definitely when X, Y, and Z, all of them can vary. That is, with respect to all the axes, I am just plotting a particular position of a particular particle, then that might include a certain amount of imaginary thing as well, because in those axes there is plus I, minus I, all those things come into picture. Only pure states can be studied in Bloch sphere, or mixed state can also be plotted. Both. It can actually, of course, you can understand that because whenever we are talking of imaginary thing, it has to be certain kind of a pure state. We will go through the details of Bloch sphere, but in Bloch sphere, the top, say, for example, the top and the bottom of the Bloch sphere, generally they present the pure states. So either it's a like high or a low, a 0 or a 1, for example, say. But the intermediate positions, or vertically it is a like pure state. Horizontally, if I just slice or make a slice of the Bloch sphere into two equal halves, then that particular axis is known as basically the XY axis. And whenever we do something with the XY axis, there will be a plus I on the plus X side and a minus I associated with the minus X axis. Plus and minus with respect to the center point. So in that way, with probabilistic amplitudes, often there can be some introduction of imaginary parts as well. And all these real part, imaginary part, they represent the respective position of those quantum state with respect to Bloch sphere. And of course, their distance, how different they are, or how much at a distance they are from the pure state, can give us very useful information. In Grover, like Shore, we will all see these things, that what from my pure state, there is up and down, how much is the deviation, that will give us different valuable information. Okay. And it changes in time means it's ultimately the time evolution of the quantum states that will give me certain output. Initially, we will start with an initial state where it's almost like a pure one. Now, let us apply that Hadamard gate, which is for the superposition. Now, once I am applying Hadamard, I'll be reaching to the stage where I have a superposed state or multiple mixed states, or one mixed state with multiple possibilities. Anything can happen. Okay. Now, on that superposed state, after time, say T1, I'm doing something. At T2 is doing something. At T3 is doing something. T4 doing something. From T4, it is again, say, going to the for the measurement or out. So all these at time Ti, what is the state of that particular quantum state is known as the time evolution. And all these things happens through Schrodinger's time equation. Okay. What is Schrodinger time equation? We will just see after 2 to 3 minutes, and that will be probably our ending for today's class. And phi xt must be normalized. Now you know all. The total probability of finding the particle anywhere in the space must be maximum 1. It can never be exceed 1. It can never exceed 1. Though here, these kind of impossible things can never happen. Right? And what if you include another particle into system? What will happen to the existing one? Just remember the concept of interference or constructive interference. In that particular case, what will happen? That is, initially I had 4 states. I had 25% probability of being in all the 4 states individually. If I add one more particle, it will be 5 states. So that means your 25% probability will also be taken down to 20%. Okay. So likewise, the total normalization, the total probability can never exceed 1. That has to be constant. That is why we use the concept of interference to increase it or to decrease it. And wave function of a free particle. A free particle is represented as plane wave. Phi xt is equals to a into e into I to the power I into kx minus omega t. Omega is the angular frequency. K is the wave number. And A is the normalization constraint. Okay. This describes a moving quantum particle with wave-like behavior. Now, time-dependent Schrodinger equation and time-independent Schrodinger equation. So TDSE, or time dependent Schrodinger equation, is actually describes how quantum state of a system, basically changes over time. So it is analogous to Newton's second law in classical mechanics, but governs the behavior of quantum states. So the equation is something like that. I into h cap into del t of phi xt, that is how the wave function changes with respect to time, okay, is equals to the h cap phi xt, where h cap is the Hamiltonian operator, which represents the total energy of the system, and phi xt is a wave function that represents a quantum state of the particle in space x, that is a location, and time t. Now h cap, which is h by 2 pi, is a reduced Planck constant. So these formula came actually from a lot of like theoretical observations and theorems and all those things. So it is really not that important that you need to memorize or some way you need to just have a like every time you will be able to write it down. Just understand the meaning that just understand the meaning of del t and the Hamiltonian operator. So how the left hand side and right hand side, they are related. So the left hand side has a component where it's a like wave function with respect to x and t and how it changes with time. So that thing will have a similar effect on Hamiltonian operator applied on phi xt, because the Hamiltonian operator itself is that operator that performs the, with respect to time, the time evolution of the quantum states. Okay. So the interpretation is this TDSE governs the time evolution of a quantum system. And if we know phi x0, which is basically at time equals to 0, we can calculate phi xt for any later time t, right? Because I'll be just putting the phi x0, then I'll be getting a certain thing, then I will be again putting the value, likewise I can actually compute. Unlike classical mechanics, where motion and another one thing, I just forgot to mention that the second point, just check it once. So if I know phi x0 at time t equal to 0, I can calculate phi xt at time later time, that is t. Now this is a very, very important claim that we are claiming, actually statement that we are claiming. What we are claiming is, if I have a wave function, its behavior, everything at time t equals to 0, we can actually calculate through this formula what will be the wave function at a later time t. So calculating means we might be able to predict the way it will work after a certain time t. And unlike classical mechanics, where motion follows definite trajectories, in quantum mechanics, wave functions evolve deterministically, but the measurement outcomes are probabilistic. Now, time-independent Schrodinger equation, that is TISE, is mostly used in order to find the stationary states. So here you can check the equation. If a quantum system has a well-defined total energy, its wave function does not change with respect its shape with respect to time, except for a phase that leads to this kind of TISE format, which is h cap into psi x equals to E into phi x, where phi x is a wave function now independent of time. That is why we're not watching that comma t thing. E is the total energy eigenvalue representing allowed discrete energy levels. For a single non-relativistic particle in one dimension, this is the formula for the Hamiltonian. And the first part represents the kinetic energy operator, and the second part represents the potential energy of the particle in space. So this is just with respect to the total energy consumption or energy like evolution, anything. Interpretation is this gives us allowed energy levels of quantum systems like electrons in atoms. It helps solve problems like particles in a box, quantum wells, and atomic orbitals. And phi x tells us that where a particle is likely to be found in a given energy state. Okay, now this is again bit important, that is application of this Schrodinger is a time evolution of quantum states. So in your brain you should be having this these four words in your mind whenever you call about Schrodinger equation. That is time evolution of your quantum states in order to go towards the output or towards the solution. That is the time evolution. So why this equation matters? So Schrodinger equation is the foundation of quantum mechanics governing how quantum systems evolve over time. In quantum computing, this equation is crucial for understanding and manipulating quantum states. Now you know why I have written the last line? Because it indeed behaves or records the behavior of quantum states with respect to time, how it evolves. So definitely it's very crucial for understanding and manipulating the quantum states. Now comes the first application, which is the superposition and qubits. So unlike classical bits 0 and 1, qubits exist in a superposition of both states simultaneously. There is time you can actually map, and Schrodinger equation describes how these quantum states evolve, ensuring controlled interference for quantum algorithms. Controlled interference means, again, second day class, I will be getting some output, but I do not know in what format I will be getting the output. So if I want to get it in my desired way, if I want to control the interference that will happen in my own desired way, then I have to do a certain kind of tweaking with the logic. So it has to be very controlled interference for quantum algorithms. That is, under what conditions I'll be going to watch for a movie, like going for a movie to watch. Either I have to ask my parents, I have to ask my in-laws, and there were like 4 stories or sub-stories I told you. So just like that, if you want to control the interference, how much they will interfere into your quantum system, then you have to make those things controlled. Application number 2 is the quantum gates and computation. Just as logic gates process classical bits, quantum gates manipulate qubits by evolving their states according to Schrodinger's equation. And this governs the transitions between states and ensuring a correct computation outcomes in algorithms like Shor's factory and Grover's search. So quantum gates and computation means basically you can manipulate qubits through some quantum gates, and whatever you manipulate, that instances or the snapshots, everything, whatever you call it, that will be stored accordingly in accordance to the Schrodinger's time equation. So that is the thing. And this governs the transition, the intermediate state evolution. So it governs the transition between states, ensuring correct computation outcome in algorithms. The third one is the simulation of quantum systems, where like Schrodinger equation allows quantum computers to model complex molecules and physical systems, making them essential in quantum chemistry as well as in drug discovery. In simulation also we need it, simply. And classical computers struggle with some simulations, but quantum computers use Schrodinger's equation to predict the molecular behavior more accurately. And application 4 is quantum tunneling and quantum annealing. Just what is a like thing? I just want to give one small resemblance so that you understand one line of it, that why it is finding optimal solutions for complex optimization problems, why this thing I've written. If you have learned simulated annealing, any one of you have learned simulated annealing, then you know that it suffers from the way it works in classical setup. It suffers from the local minima or local optima trap. So it gets trapped somewhere into the system. So it cannot really go for the optimal solutions or the global solutions. Okay, so that was the idea of a simulated annealing. Now, quantum physicists have seen that, okay, so if I want, because quantum has a property to behave as both the classical as well as, both the waves as well as particles. What if I say that I have a huge playground? It is it is that ground of mine where I can say that there is a big rope just lying on the floor. That rope represents a quantum wave. And I'm telling that I can actually plot a value over here. That is also my solution. I'll be plotting a value over somewhere at a distance of say 50 meter, at a distance of this. Likewise, because it's a wave, wherever I want to, I will be putting that particular thing probabilistically, keeping that it is a quantum wave of rho where multiple possibilities can be encoded. What is the benefit of it? If I am able to do that, can I not say that wherever position I am into, if I just look into the entire quantum equation, I will be able to say that what will be my output, taking a look onto all the solutions. So it is no trapping into local optimum because it is behaving like optimally. It is behaving like a duality principle, particle and wave both. So if I am able to encode all possibilities together on the floor, then at any point of time, I can actually see all those other points. So by watching all those other points, I will be easily get rid of being trapped into the local optima and actually go for a greater solution, which is the optimal solution. That was the target. And it is very, very much useful for complex optimization problems. And this concept where through probabilistically we believe that we can tunnel through between multiple possibilities, we can tunnel through. This concept is called quantum tunneling. And D-Wave is one company which basically works on the similar principles of quantum annealing. Just last 2 points. Application 5 is error correction in quantum computing. So quantum error correction relies on understanding the quantum does tunneling. Absolutely. It helps in locating all the local minimas so that now there is a technique now. So maybe that will come later once we know it. But it will encode all possibilities. So there is no way where I can stuck into one local optima. Okay, and now which is the, say for example, I want to encode cost. Now there is a technique known as the adiabatic process. So it's also called adiabatic model of computation. This simulated annealing, quantum tunneling, all those things. So very adiabatically, I have to tune my algorithm in a way so that whatever is the minimum lowest energy quantum state, lowest energy it possesses, that will be associated with the best solution. Likewise, we try to encode our problems onto a quantum annealing. Okay, and in error correction, I was just telling that Schrodinger's equation helps in designing the quantum codes that preserve information despite noise and decoherence. Sorry, what was your question? Are you telling to explain annealing again, maybe? Okay. Please note it down. Just one more minute. I will take. That is for the quantum communication and cryptography. Yes, okay, I will explain. Quantum communication and cryptography. So here also there is a secure key exchange mechanism. There is quantum internet. There is quantum communication where multiple quantum states varying as a certain inputs are being transferred from one place to another. So for all those things, it is definitely basically using Schrodinger's equation. Yes. Now, what was your question? Deepak was asking some question, I guess. I'm done for today's class. Let me just stop sharing. Then, so tunneling is a result of TDSC or TISC or both. It's actually, tunneling is associated with both. It is absolutely associated. It's just encoding all the possibilities together. Instead of the way how it works for a gate model or the way we are talking about IBM, all those companies except the wave, it's a finally after you have the encoding, how you will be interpreting it. But once it is like an annealing mode or quantum annealer, it works on the principles of adiabatic physics process. So let it just cool down. So once it is cooling down, eventually all the energy states which is have a excited states of energy, they will all be actually diminished. So ultimately, at the very bottom, I'll be getting that particular value which is associated with the minimum quantum state. Okay. Yes. So time series forecasting. I think this is very abstract level, whatever you are asking. whether you can use it or not, any problem, just forget about time series forecasting only. Anything, if you want to encode using quantum, you have to think of doing it, or the feasibility study you have to do that. Two things you have to check first. Can it be done on real time? Whatever hardware you have or the way you encode, will it really work in accordance to your business requirement? That will be the first thing. Otherwise, it is of no use. You have to then think of some alternative computing, where maybe a component of it will be doing using quantum, and the rest will be following the previous one. And the second thing that you have to take care of is, even if you have the hardware and all, are your algorithm good enough to encode it? Are you able to be able to successfully encode the system into your quantum computer? Then only the concept of like whether you can apply a time dependent or an independent Schrodinger will come into picture. First, you have to think of how you can encode it. If you can encode it, then it will happen. No issue. It all depends on you. So there is no hard and fast rule. You have to do that research. Share my email ID. You can follow or ask me questions on LinkedIn. That is where I'm like mostly available, Devender.
Ma'am, we are trying to look at creating the this thing on Canvas. Hopefully, if we are able to do that, then there is a forum there so that people can post question and you can reply at your leisure. I think that is one option. Of course, LinkedIn is. I mean, again, there may be many more people who may keep on asking questions. So we'll try to focus on the content that is being covered here. So we can keep the restriction to the forum. There is another WhatsApp group, but I think there is a lot of discussion going on. So you may be overwhelmed actually. But then we will encourage them to come to Canvas. So that way both purposes will be served. Right? Yeah, sure. Okay.
Okay. Thank you, participants. I think we're done for today. Hope to see you all tomorrow.
Yeah, thank you, Dr. Nivedita. We are on time. We have concluded at 4. We started at 2. So hopefully we'll have meaningful sessions like this for the next period. Most of you have joined, and there is no issue now by and large, except for a few Canvas things. We'll try to sort this out, and we will meet tomorrow at 2 o'clock. Thank you so much. The YouTube link will be shared. The slides will also be shared immediately, shortly in some time. Right? Thank you so much, and please look up